Hello, welcome to Calculus. I am back in my recording location from the first several videos, so hopefully traffic will not be a problem this time. Today, we are going to be making the transition from limits into continuity, and our route for that transition is going to be the Squeeze Theorem. Now, the Squeeze Theorem has, of course, a mathematical definition and meaning and all of that, but I think it's easiest to just sort of build up to it in more vernacular. So the first thing that I want you to do is picture a graph in your head. Any graph that has some curvature to it. So for my example, I'm just going to draw some axes over here. I'm going to do a graph that looks something like that. Let me actually go back and do that in a different color. So similar graph, probably going to be a little bit different. But there's my graph. Now, think about another graph that on the interval you're imagining in your brain, it's completely under it at all times. So we don't care what it does outside of our frame of reference. But at the section of the graphs that we're looking at, your second, so in my case, it's going to be my yellow graph, your second graph is less than or below your first graph, my red graph, at all times. Or at some point, it can be equal. So mine's going to be equal right there. And then it's going to go off, do something else. So we know for a fact, because we decided that this red graph stays greater than or equal to this yellow graph the entire time in this frame of reference. They might intersect and cross each other outside of this frame of reference, but for the Squeeze theorem, that doesn't really matter. Now, I'm going to take a blue graph, and let's say that we know it is between the red graph and the yellow graph at all times. It is never greater than red, and it's never less than yellow. Well, if it is, and again, that's just for the frame of reference that we're talking about. Well, if there is a point right here where red and yellow equal each other, then blue at that same point must be equal to red and yellow, right? And say there's a discontinuity. So say blue looks like this, but then we have one point of blue up here, and then it goes back down to being normal. Let's start to think about that through the context of limits. So red does like this, and then right here, it sort of merges on that point. Yellow does the same thing. It stays fully below red, but then they merge at that one point. Now, even if they equal something else, remember that limits don't really care about what they equal. They're more about predicting what they will equal. So this, as we've defined it here, the limit of red as it approaches this black dot is equal to the limit of yellow as it approaches this black dot. Now, think about blue. We said, we defined ourselves that blue is always, always, always between red and yellow. So it's less than or equal to red, and it's greater than or equal to yellow. Well, right here, its limit must be equal to the limit of red and yellow, right? Because if red and yellow have the same limit, how can blue have anything else and still have any other limit and still be between them? And that's what the Squeeze theorem says. It says that as these two top and bottom graphs squeeze together the middle graph, their limits are all going to be the same at the point where the top and the bottom are the same. For that reason, it's also called the sandwich theorem, because it says that the top and the bottom are sandwiching the middle one into place. And the mathematical definition is a little bit more complicated. We will get into it. Do not worry. All right. So what I have done is I have written out the formal definition of the squeeze theorem. And I may have simplified it some, but this is the essence of it. This is it entirely based on a more than necessary level of understanding. So if f of x is less than or equal to g of x is less than or equal to h of x on some interval a, b, except for possibly at some point c where x equals c, and the limit of f of x as x approaches c is the same as the limit of h of x as x approaches c, then the limit as x approaches c of g of x equals the limit of x approaches c of f of x, which we already said equals the limit as x approaches c of h of x, is what that should say, although it says g of x right now. So I'm going to go through and fix that. I'm going to try and keep talking while I do so. So this has some important implications for solving limits if you have them graphically. But more than that, I think it is a great way to start thinking about how things are going to work in calculus. Not a lot of things are going to be defined axiomatically. So that means not a lot of things are a certain way just because that's how they are. Like, addition is addition is addition. And the reason that addition works the way it does is because axiomatically, addition is defined to work that way. If you do something else, it's not called addition. And if addition didn't work the way that it does, the rest of math would change. It's the same thing with graphs. If graphs worked some other way, and there are systems that are currently being studied by professional mathematicians where graphs do work different ways, but if graphs worked some other way, then all of algebra and all of geometry would be different. Whereas theorems, Pythagoras theorem is a great example of one that you probably already know. Theorems are things that we can prove based on the axioms that are already set. So an axiom is something that is the way it is because it has to be in order for math to work, whereas a theorem is something that you can prove based on the axioms that you have set. And this is a really important lesson that I have learned recently. And that lesson is, if you wonder why something is assumed and it's not a theorem, then change it around. See if you can make a system that works with some different axioms. I know that Euclidean geometry, people love changing Euclid's axioms of geometry and seeing what happens from there, and it's a fascinating field of study. So see if you can, in your own personal study, for your own enjoyment, use axioms, change them around, and see how math changes. That's one of the most rewarding ways to study math, and it's also one of the most useful. So while knowing the squeeze theorem is useful, knowing why the squeeze theorem works and being able to think about math using theorems instead of just using axioms and things that your teacher tells you, being able to think critically about the way math works is even more useful than knowing the squeeze theorem on its own. So yes, definitely study this, memorize this, practice solving some limits with this, but also practice thinking about math in ways that you wouldn't normally. This is Quillen praying that you continue with me on this journey through calculus. Praying also that you continue to be curious about math. This is Quillen signing off. I'll see you next time.